Okay, here we are back again. We're going to talk a little bit about the mathematics of series circuits. As you can see here, I've drawn a picture of a power supply connected to 3 resistors, which we now have talked about in the last video, that they're considered to be in series. 10 ohms, 20 ohms, and 30 ohms. If the power supply is 60 volts, which we're going to do the same kind of circuit for all 3, a series, a parallel, and a combination. Let's start with the series. We said that the total resistance is going to be all 3 added together. So 10 plus 20 plus 30 gives you a total of 60 ohms of resistance. The next thing we could find is the total current, which by Ohm's law would just be the total voltage over the total resistance. Total voltage being 60 volts, and now we just found that that's 60 ohms of resistance. Made the problem easy to give us a total current of 1 amp. 1 amp of current in that. That means out of the power supply you're going to get 1 amp. And what we learned in the last video was if you put an ammeter any spot along here, doesn't matter whether you chose here or somewhere in the middle, you're going to get 1 amp for each one of them. So that's the current through R1, R2, or R3. The next thing would be to calculate what is the voltage drop across each one of those resistors. We said that the voltage is additive. So let's go ahead and calculate what the voltage for any one resistor. That would be the total current times the resistance. Total current being 1 amp times 10 ohms gets you 10 volts. Whereas if you keep doing it for the different resistors, it'll be the current times the resistance. It'll be 1 amp times 20 ohms gets you 20 volts. And the third one, the total current times R3 gets you 30 volts. So the voltage across R1 is 10, voltage across 2 is 20, and that of 3 is 30. If you add those together, you get the total of 60 volts. But if you think about it, that's just the total current times the total resistance. 1 amp times 60 ohms is 60 volts. So if we think about that, it works out pretty nicely and it seems to make sense. Things to remember, the current is the same for the resistance. The resistance total is additive and the voltage is additive. The other thing about this total resistance is the total resistance is higher than any one of the given resistors in that circuit. So by adding up another resistor, what that does conceptually is adds more ability to stop the current from flowing. And that makes sense. Let's do the same thing. We'll call it a parallel circuit. So we have the same 3 resistors, 10 ohms, 20 ohms, 30 ohms, but they're in a parallel combination here. They're all effectively connected across the power supply. So what we said was that they're going to get the total voltage of the power supply. So if you hook them up to a voltmeter, you would get 60 volts measured for each one of them. They're going to be able to use up the total amount of energy supplied by the power supply. Now the current is something that you can figure out by taking a look at the total resistance. But we said that the total resistance is reciprocal additive. So go ahead and let's take a look at it. Now mathematically, we can take a look at this. If we put in 1 over 10 and 1 over 20 and 1 over 30, we'd have to find a common denominator, and the common denominator might be 60, so see if you agree with 6 over 60, and then that would be 3 over 60, and 2 over 60. Sure enough, when we add those together, add those on the top, we get 11 over 60. But that's equal to 1 over our total. So if you want to know what our total is, you have to take the reciprocal of both sides of that, and that would be 60 over 11 ohms. 60 over 11. Think about that for a second. In the last slide, we said that the total resistance for series was greater than any one of the resistors. Here, the total resistance is less than any one of those. 60 over 11 is less than 30, 20, or even 10 ohms of resistance. So that's something significant. You're getting a lot more current in this type of circuit. And let's find that out. Let's calculate the currents. We could take the voltage divided by the resistance, 60 volts over 60 over 11. I chose to keep those in fractions so that you could see that that's a total amount. Excuse me for saying that's the total current in that would be 11 amps. For each one, we take the voltage divided each one resistor. This would be 60 over 10 is 6 amps. For 2, that would be the voltage divided by the resistance. And that would be 60 over 20, which is 3 amps. And you could see for the third one, if I just go across, that will just be the voltage divided by its resistance. And sure enough, that's 60 over 30, which is 2 amps. If we add all these together, 6, 3, and 2, sure enough, we get the total, which is 11 amps. So each one of those pieces adds up to the total. And if we go back to the top picture there, 11 amps is what comes out. And so we're going to say that 6 of them go this way, 3 go that way, and 2 go there. So that gives you the total of 11. Hopefully that makes some sense for a parallel. Our job is to then take a look at what happens for the combination. For a combination circuit, let's do the same thing. We have the same 3 resistors. It's just we have R1 connected to the power supply in series with it, but then R2 and R3 are in parallel. So I think let's take a look at what happens with the parallel. If we just wanted what's happening with those 2 resistors, we could say 1 over the equivalent resistance between those 2 would be 1 over 20 plus 1 over 30. If we just do those 2, that's the same as 3 over 60 plus 2 over 60, which is 5 over 60. Remember, though, that to find the total resistance, we have to take the reciprocal of that. So that would be 60 over 5, which is 12 ohms between those 2. By the way, the term equivalent resistance comes from the idea if you took one resistor and put it in the place of those together, that resistance would replace the 2 and give you the same amount of current. So it's the equivalent of having just one resistor. The total resistance overall, though, would just be R1 plus that equivalent resistance, and that would be 10 ohms plus 12 ohms for a total of 22 ohms of resistance in that circuit. What does that give us for a current then in the circuit? That would be the total voltage over the total resistance, 60 volts over 22 ohms. And if you do that, you get 2.727 amps of current. That's the total that comes out of the power supply. Up at the top of that picture would be somewhere around 2.73 amps. How much voltage then would be here versus anywhere else? The voltage in the first resistor is just the current times the resistance. That first resistor sees the total, so you could take the 2.727 amps and multiply by 10 ohms, and sure enough that would give you 27.27 volts. What does that leave for the other 2? So the voltage 2 has to be equal to whatever it is for 3, because those 2 are now in parallel, would just be whatever's left from 60. So 60 minus that, if you do that, that's going to give you like 32.73 volts. And then you could take one last step to find out what the current in each one of those, the current in the second resistor would be the voltage divided by the resistance. We just said that it was 32.73 volts, and we divide by 20 ohms, which is the resistance of that, and that gives you 1.636 amps. And if we did the same thing for the third resistor, that would just be the voltage divided by the resistance of that resistor. Take your 32.73 volts and then divide by 30 ohms, and sure enough, that's 1.0909 amps. And when I say sure enough, I mean when we add these two together, sure enough, we get 2.73, which is the total current. So that's the way a series, parallel, and combination circuits act with the same resistors. You get different currents in all the three cases, and that gives you some idea when we're doing problem solving individually, or we solve and I assign some other problems, how you're going to look at finding voltages, currents, and resistances for the various circuits that we give. I hope this was helpful. Again, stay healthy, and we'll see you next time.